Hi folks. Start doing a little math. Little math never hurt anybody. That's what I think. I don't know why I don't have my setup ready. Don't. Alright. Jeez. This is live stream. This is rinky dink, and I don't claim to be very polished here. But we're going to just pound out some integrals. Okay, it's our old friend e to the u. We love e to the u. But the way I'm going to get that is if I pick u equal to minus x squared. And when I do that, I get e to the u by design. And du is minus 2x dx. What I have left to substitute for is that x dx. I can get that right here. X dx is equal to minus 1/2 du. I'll put the minus 1/2 there. I'll put the du, and I'm ready to go. I have negative 1/2. Oh, let's getting ahead of myself here. Let's do the bounds. Okay, so I was going from 0 to 1 when we were in x, but we've now switched to u, so let's be real careful here. When x equals 0, u equals 0. I'm plugging in right here for x. Okay, so u is 0, and then when x equals 1, u equals negative 1. Put a negative 1 there. Okay, then we'll integrate. I get negative 1/2 e to the u evaluated from 0 to negative 1. If it bothers you that it's backwards here, you can switch it, but you have to put a minus sign out in front. So negative 1/2 e to the negative 1 minus e to the 0. E to the 0 is 1. My final answer is negative 1/2 1 over e minus 1. See if you believe that. See if I believe it. I believe it. Number 61. Oh, this one's kind of Mickey Mouse, a little gimmicky, but that's okay. It's trying to remind you of an idea, and might as well get a little refresher on that. The reason I say it's Mickey Mouse is just it's very specific. You know, you're really trying to illustrate a point, making up a problem to fit it. And also, if you're new at it, you're going to not like it. You're just going to say, okay, that's fine, but I'm just not ready for that. And it is true. If you're at a certain level, you're just not ready for these kinds of things. You don't care, okay, about odd functions and even functions. You just want to get practice with your antiderivatives. Okay, and this one here can't be done. So this is the last thing you need when you're trying to learn how to do integrals, is for them to give you an integral where you can't do it. You're just spinning your wheels trying to figure it out. The design of this is to realize that this is an odd function. The whole thing is an odd function. And the picture for an odd function is something like this, where you have the same stuff on a mirror image or symmetric about the origin, where the y value here is the same as the y value here, and here would be x, and here's negative x. So if you plug in x and you get y, then when you plug in negative x, you get negative y. That's the symmetry, and that can be written out in functions. The check for oddness of a function. An odd function has the property that f of negative x equals negative f of x. Okay, and if you're a normal person, when somebody gives you that kind of information, it doesn't really mean a whole lot. You're just looking at it as symbols, okay? And it takes a little bit of thought to really connect this picture here with the symbolism. And we can do an example. Let's just do a quick one, like x cubed is an odd function, and this picture here is a lot like x cubed, maybe x cubed, right? But x cubed is a good example of an odd function. So if I have f of x equals x cubed, and we pretend for a second that we weren't told that it was odd, and we want to check it, this is the check right here. So if I take f of negative x, I put it in there, that's going to be negative x cubed, right? That's what happens when whatever I have here, I put it in there. Okay, and then when I let the negative 1 have the third power, that just gives me a negative x cubed. And isn't that equal to negative f of x? You see, so it satisfied that condition that f of negative x equals negative f of x. You see, here's the length f of x, so this is negative f of x. And it's saying if you plug in negative x, you should get the negative version of what you got if you plugged in f. Sorry, if you plugged in x. Okay, anyway, that's a good thing to just sit there and think about why this symbolism here checks this fact, that the y value at x should be the same length as the y value at negative x, just going in the opposite direction. All right, well, anyway, when you have an odd function like this, integrals are calculating area, and when you go from the same place, because we're going here, here's 0, and we're going from negative pi over 4 to positive pi over 4. So we have the same amount of length on the left as the right, but we have an odd function, so something like this is happening. The integral is calculating area for it, or net area, and we're going to get a positive area, and we're going to get a negative area, and they're going to cancel each other out. If you have an odd function, this will be 0 because we're having the same distance from 0 on each side. Okay, so that's the design of the problem. Now, let's check. Let's be real careful here. We have f of x equals x cubed plus x to the 4th tangent of x. And we want to check and see if this is odd or not. Well, the check is over here. Here's my decoder ring right there. Okay, I'm going to dip this function into a vat of liquid, and it changes color, then it's odd. Okay, and that little vat of liquid is this test right here. I'm going to go f of negative x equals, well, I'm just going to be real detailed about it. I'm putting negative in there, negative x in there, plus negative x to the 4th power tangent of negative x. That's what it means to have f of negative x. And I'm looking to see if that happens to be negative 1 times f of x. Okay, let's see if we get that. This one becomes negative x cubed. And then the negative 1 here to the 4th power just becomes positive 1. So I still get plus x to the 4th. But what about the tangent of negative x? Let's go off to the side here. Tangent of x is equal to sine x over cosine x. And so tangent of negative x is sine of negative x over cosine of negative x. And maybe you remember identities from your trig days, maybe you don't. But let's just take a look at these, because these come up a little bit here and there in calculus. Here's our unit circle, kind of a bad one. Okay, and there's our angle. So this would be the positive x, and this would be the negative x. So you see, and here's, let me redraw this. I'm not very happy with it. Okay, let me see if I can do a better job here. All right, here's our unit circle, and then we're looking at the angle here. That would be x, and then if I go the opposite way, that's negative x. And at these angles, here's the sine of x, and the cosine of x is right there. So you see how the cosine of negative x is the same as the cosine of x. So that's the same. Let's write a little bit more here. So tangent of negative x is equal to sine. Let's rewrite this better. There's a little, I'm going off on a tangent, pun intended. If I have tangent of negative x, that's sine of negative x over cosine of negative x. Okay, but cosine of negative x is the same as cosine of x. So this negative can be ignored. So this is equal to, on the bottom, it's just cosine of x. And then sine of negative x, you see here's negative x, and sine of negative x, well, you see, it's negative sine of x. Sine is also an odd function. Okay, so maybe you remember that as an identity. Maybe you can see it here. Maybe I've just confused you more. But all in all, what we realize here is that tangent of negative x is negative tangent of x. So tangent itself is an odd function. But more importantly, I'm going to go put that in here. Tangent of negative x is negative tangent x. This becomes that. I can pull the negative out. It's an odd function. Okay, well now what do I have? I have negative times x cubed plus x to the fourth tangent x, because this negative here and this negative, these two get brought out in front. And that is negative f of x. See, f of x was this. I plugged in negative x, f of negative x. I played around with the algebra. I realized that tangent x is an odd function. I realized that x cubed is an odd function. And then I was able to factor that out, and I got negative f of x. So it satisfies that test. Okay, so then since it's odd, I don't care what it looks like. It's blah, 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 and blah, 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 blah. But whatever I have on this side, I'm going to have the same on this side. And so when you go from negative pi over 4 to positive pi over 4, they cancel. You get negative area, positive area, so the net area is 0. And that's the answer. And that's since f of x is odd. Okay? And that's odd as in odd and even, not odd as in strange. But it's a little bit of both, probably. That was number 61. Yes. Not too many of those. They throw a few of these in there. You can kind of spot them because they have this configuration. It's not always the case, but that's a good first guess, I think, when you see the negative pi over 4 and pi over 4. You know, maybe on a test you might want to be suspicious that that's an odd function. Then you got one of these little tricky ones. Okay, number 62. We've got 0 to pi over 2. Cosine x, sine of sine x. Cosine x, sine of sine x. A lot of times, even if you just took a trig class, you've never seen anything like that. That even just kind of boggles the mind to the sine of sine x, right? But only in integrals do you see that kind of stuff because they're rigging it so you can practice your integrals. Okay, so the design here is that you want this integral to become sine of u. You're going to pick u equals sine x, and then you'll have this sine of u inside of it. And guess what? The derivative of sine x is cosine x, and that's sitting right here. So it's a good choice. U equals sine x, du equals cosine x, dx. Okay, let's substitute for everything we see here. We have sine, this sine, and then here's u. So I have sine u. And then the cosine x dx, that's just equal to du. Okay, then let's switch the bounds. When x equals 0, u is equal to 0. when you plug in x equals 0 for in sine of x. And then when x equals pi over 2, u equals 1. So this integral is going from u equals 0 to u equals 1. Integrate. The thing whose derivative is sine u is minus cosine u, because the derivative of cosine is negative sine. So if we want to get back to positive sine, we better have a preemptive strike of a negative sitting there. Okay, that's going to be evaluated from 0 to 1. No need to go back into x. So that gives me negative. Okay, don't try to be a hero. Just leave that negative out there. You can even put a little thing there to remind yourself. Then I get cosine of 1, which is not so comfortable to look at, minus cosine of 0. Okay, so that's minus cosine of 1, and then cosine of 0 is 1. Okay, cosine of 1 is not one that we know. We know things like pi over 3 and pi over 4, pi over 6, but not 1. This is 1 radian. So you just have to leave it like that. You can put it in your calculator if you like. But I guess if we cleaned it up a little bit, we could get 1 minus cosine of 1. That's about the best I can do. That was number 62. Let's do 63. Number 63. Get a little practice on our cube roots. We're going from 0 to 13. That can't be random. That's going to help us do the cube roots, I hope. Dx on top, and then on the bottom I have the cube root of 1 plus 2x. And it's 1 plus 2x squared. So there's a lot of stuff going on here. If it helps you, rewrite this as 0 to 13 dx over, we can get rid of that radical, that the cube root part, and write it all as an exponent. This is 1 plus 2x to the 2/3 power. Okay, I've got the 2 here, but then a cube root is a 1/3 power. Which is, of course, when it's in the denominator, that's a negative 2/3 power. Okay, but you see, you can do that, right? You can do anything u to the n du, where n is, as long as it's not equal to negative 1, well, you can even do that one, because that's 1 over u. Du, but this thing, you just add 1 and divide by whatever you get after you add 1. So we're going to do that with negative 2/3 here, but first let's get a u substitution going so we don't have to deal with the 1 plus 2x. That's the purpose of the u substitution. I'll let u equal 1 plus 2x, then du is equal to 2 dx. The integral then converts to on the bottom, I have u to the 2/3, and in the numerator, all I have is dx, but dx is 1/2 du. Put the 1/2 out here, put the du on top. Okay, if you like, you can write that. I'll do that in the next step, but you can write it as u to the negative 2/3. Let's switch the bounds. When the problem was given to us in x, it was from 0 to 13. So when x equals 0, u is equal to 1, because I'm plugging in x right there. And when x is 13, well, then u is equal to 27. I'm plugging in the x right here. I get 26 plus 1. Okay, u is 27. Look at that. Oh, yeah, that's getting ready for a cube root there. That 27, isn't it? Okay, let's finish it up. Let me just rewrite it so we see what we're about to do. I'm going to do u to the negative 2/3 du, because a 2/3 exponent in the denominator is the same as a negative exponent. That's 1/2. Don't try to be a hero. Just leave it out there, and maybe So what am I going to do? I'm going to add 1 to the exponent, which is the same as adding 3 over 3. So I'll get u to the 1/3, and I'm going to divide by that very 1/3, which is, I'm writing it there, but I'm not going to keep it there because it's so ugly to look at. But that's the same as multiplying by 3. Okay, when I divide by 1/3, it's the same as multiplying by the reciprocal. Okay? And that's all going to be evaluated from 1 to 27. Not too bad. I have 3 halves, and then I have the cube root of u evaluated from 1 to 27. So that's 3 halves times, when I put in 27, I get 3. And when I put in 1, I get 1. How about that? So look at that. That gives me 3 as my final answer. What a nice, clean answer for such a messy problem. Okay, that was number 60-something. That was 63. Yeah, that's a good one for you to do all by yourself. Just go through and from beginning to end without looking at all. And if you have to look, it's okay, but then if you look, then stop and start all over again and go from the very beginning to the very end. All by yourself and get the answer, and you'll feel really good about it. And that's how you start getting your brain to look ahead and see how these. You got to work all the little details out yourself so that your brain can download this information. All right, we've got a red problem here. I don't know why it's red. It's kind of annoying. It's got this A in it now. I wrote it in the wrong place. So it's the integral from 0 to A. X, and then I've got a squared minus x squared dx. Okay, now this is a little bit of a confuse the enemy situation. I do think they even qualify for A. Do they say something about A there? I don't say anything. Okay. Well, it's a confuse the enemy situation because we've got X's and A's, but don't let the A throw you off. The variable is X. Okay, the variable is definitely X. There's only one variable. A is not a variable. A is a constant. And you say, well, if it's just a constant, then why do you have A squared? Well, because they have A and they have A squared. So if this was 3, then this would be 9. And if this was 4, this would be 16. And this comes from the square root thing comes from a circle. But anyway, they rigged it. They put this x out in front so you can do the integral. Let's do this. We would love to have square root of u, wouldn't we? Let's say so that we have square root of, right? We know how to do that. So u equals a squared minus x squared. Then du. Remember, a is just a constant. So when you take the derivative, it's 0. Derivative of negative 2x is minus 2x, sorry, negative x squared is minus 2x dx. So when I convert this integral, the square root of a squared minus x squared, that's just square root of u. Then I still have that x dx to account for. So I get it right here. X dx is minus 1/2 du. Put a minus 1/2 there, put a du there. And now let's do the bounds. When x equals 0, u is equal to what? Well, if I put in x equals 0 here, I get u equals a squared. That's not so comfortable, but that's what we got. When x equals a, u equals 0. So I put x in right here. I mean, when I put in a in right there, I get a squared minus a squared. So there's u equals 0. Ready to go now. Negative 1/2 Okay, again, integrating root u, we're going to get u to the 3 halves. It's 1/2 power plus 1, which is the same as adding 2 over 2. So 1/2 plus 2 over 2 is 3 halves. And we divide by that 3 halves, but who wants to do that? That's the same as multiplying by 2/3. And we're going to evaluate that from a squared to 0. Okay, a little housekeeping. We get negative 1/3. And then I plug in the 0, and I get 0 for u, minus, now I plug in the a squared. Let's go off to the side and get this right. I have a squared to the 3 halves power, so that equals a cubed, because the 2's cancel. So I have, when I plug in the a squared, I get minus a cubed. And then all told, the minuses cancel, and I get a cubed over 3. That's the answer. A cubed over 3. How about that? That was number 64. Number 64. That was number 64. Okay, I'm going to stop. That's plenty for now, I believe. What did I do? I only did 60 through 64. I feel I want to take a break because I'm hungry. So live stream ends and I'll come back and finish a little later. But nobody comes to my live streams anyway, so it's just me here. I can do what I want. But someday I'll have people and I'll have to stay even though I'm hungry. Okay, I'll see you in the next video, or I won't, and you won't even see me, so that's a terrible thing to say. You'll hear me in the next video.